Welcome back to the deep dive. Today, we're plunging into a field that feels, well, a bit like science fiction, but it's rapidly becoming a reality. Multimodal large language models, or MLLMs. We're going to unpack their profound implications for medicine, particularly how they're reshaping education and clinical practice. Imagine a future where AI isn't just reading medical charts, but actually seeing x rays, perhaps hearing patient symptoms, and then reasoning across all of that information simultaneously. That's the revolutionary promise of MLMs. We'll be exploring not just how these models are built and what they're capable of, but also the vital ethical framework needed, to ensure these powerful tools serve humanity responsibly. For you, our medical professionals listening, this deep dive is really about understanding how these innovations could transform your day to day, from diagnostics right through to lifelong learning.
Indeed. And what's truly fascinating here is that we're moving beyond traditional AI, which typically focused on processing single types of data. In isolation, really, MLLMs represent a real qualitative shift. They're capable of interpreting diverse data types simultaneously, whether it's text, images, or even audio signals. This convergence has immense potential to unlock insights we simply couldn't access before. But, well, as with any powerful tool, understanding its nuances and establishing robust ethical guidelines is absolutely paramount.
Okay, let's unpack this then. We're talking about systems that can see and hear, as well as read and write. It sounds almost too good to be true, doesn't it? Could you start by giving us a foundational understanding? What exactly are multimodal large language models, and how on earth do they manage to bring all these different senses together?
Fundamentally, an MLLM is essentially a large language model. You can sort of think of it as the brain of the operation, exceptional at understanding and reasoning with text, but now it's been equipped with eyes and ears. These sensory organs come in the form of pre-trained modality encoders, like image or audio encoders, which are specifically designed to receive and pre-process optical or acoustic signals, the raw data. The crucial part, though, is how these different senses talk to the central brain. That's where the modality interface comes in. It's the ingenious link that aligns all these diverse inputs, projecting the information into a format that the large language model can seamlessly understand and, well, reason with. Some MLLMs also have an optional generator that can output things other than text, like images perhaps, truly making them full-spectrum communicators.
That's a very clear analogy. So these modality interfaces, they sound like incredibly clever interpreters. How exactly do they bridge that gap between, say, an image of a lesion and the text-focused large language model?
Right. Well, we primarily see two main types of learnable connectors for these interfaces, what we call token-level fusion and feature-level fusion. With token-level fusion, the features extracted by the image or audio encoders are transformed into discrete tokens, much like words in a sentence. These new tokens are then simply added to or concatenated with the text tokens before the entire stream of information is fed into the large language model. A very common and effective approach here involves learnable query tokens, first implemented in a model called BLIP2, which efficiently compress the visual tokens into fewer, more manageable representation vectors. Other methods might use a simpler, small neural network, like an MLP-based interface you see in the Lava series, to align the feature dimensions directly with the word embeddings the LLM already understands, sort of a direct translation. Feature-level fusion, on the other hand, allows for the fusion of these different modalities directly within the large language model itself, often by subtly modifying its internal architecture to accept these diverse inputs. What's truly remarkable about these interfaces is their sheer efficiency. Imagine a tiny, almost invisible bridge connecting two massive continents of data. That's really what we're seeing. For example, in a model called QuinVL, the interface, the Q-former bit, is less than 1% of the model's total parameters. The encoder and LLM make up the vast majority.
Less than 1%. Wow.
Exactly. And this isn't just a technical curiosity. It means we can build incredibly powerful multimodal systems without having to retrain or massively expand the core LLM, making them more agile and scalable for, real-world medical applications.
A tiny bridge for a huge amount of information. That's quite a feat of engineering. It makes sense that these connections are optimized, but I'm curious, beyond these clever learnable connectors, are there any other ways researchers are trying to get different modalities to talk to each other, maybe more straightforward ways?
Yes, absolutely. Another approach is to use what we might call an expert model, perhaps a pre-trained image captioning model, for example. The core idea here is to convert multimodal inputs, like an image or a video, directly into language without requiring additional training of the large language model itself. For instance, there's a system called video chat text. which leverages pre-trained vision models to extract visual information, like identifying actions in a video maybe. And then it enriches these descriptions using a separate speech recognition model to transcribe any accompanying audio. Now, while this method is quite straightforward to implement, it can sometimes lead to information loss. For instance, transforming complex videos into just textual descriptions can distort crucial spatial-temporal relationships, the timing and location of events which are often vital for a full understanding in many medical contexts.
That makes perfect sense. You lose some of the nuance in translation, I suppose. So the interfaces are these clever bridges, but what about the core brain of these MLLMs, the large language models themselves? Are we building them from the ground up for these new tasks or leveraging existing powerhouses?
Well, it's far more efficient and, frankly, practical to start with a pre-trained large language model. These models have already undergone extensive pre-training on vast web corpuses, meaning they come embedded with rich world knowledge and possess strong generalization and reasoning capabilities right from the get-go. Most commonly used large language models are what we call causal decoders, essentially. They're designed to predict the next word in a sequence, which makes them excellent at generating coherent and contextually relevant text. Notable examples include things like the Flanty 5 series, the Llama series, Vicuna, and Quen, which is particularly interesting as it's bilingual, supporting both Chinese and English quite effectively, making it globally versatile. What's truly exciting is the impact of scaling up these pre-trained LLMs. Studies have consistently shown that simply scaling from, say, 7 billion to 13 billion parameters, or even further to 34 billion, can lead to comprehensive improvements across various benchmarks. It's almost as if the model gains deeper insights with more internal connections. What's more, with a 34 billion parameter LLM, it can even show emergent zero-shot capabilities in other languages.
Zero shot, meaning it can do things it wasn't specifically trained for?
Exactly. It can perform tasks in a language it wasn't explicitly trained on for that specific task, just based on its general understanding. There are also ongoing efforts to create smaller LLMs, such as the mobile VLM series, which use downscaled Llama models. This enables efficient deployment on mobile devices or more localized systems. And that's a huge step for accessibility in diverse medical settings, places without massive server farms.
So the sheer scale makes them smarter and more versatile. And what about this mixture of experts approach you mentioned? It sounds intriguing. How does it actually make these large models even smarter and more efficient, especially for us in the medical field?
Ah, yes, MoE. That's a fantastic question, and it's a very promising area of development. Mixture of experts, or MoE architectures for LLMs, are a rather clever way to scale up the total parameter size of a model without proportionally increasing its computational cost. Imagine you have a team of highly specialized consultants, and for any given problem, you only consult the specific specialist whose expertise is most relevant.
Okay, makes sense.
That's essentially what a MoE model does.
Yeah.
It selectively activates only a fraction of its total parameters for any given input. This sparse architecture means it's incredibly efficient. And what's really exciting here is that models using this MoE approach, like MM1 and MoE Lava, are actually outperforming the more traditional, dense models on almost every benchmark.
Really? Better performance and more efficient.
Yes, all while being more computationally efficient. It's like getting more power for less effort, which is, well, a huge step forward for deploying these models in resource-constrained environments or for demanding real-time medical applications where speed and efficiency are critical.
So the architecture sets the stage for remarkable capabilities. But how are these MLLMs actually brought to life and refined for specific tasks, especially in a sensitive domain like medicine? What are the key stages in their training journey? It sounds like a long process.
It can be. The training of a full-fledged multimodal large language model typically involves three distinct stages: pre-training, instruction tuning, and alignment tuning. Each phase serves a unique purpose and requires different types of data, building on the capabilities of the last. The initial stage, pre-training, is all about teaching the model to align different modalities and acquire a broad multimodal understanding of the world. Think of it as teaching a child to connect words with pictures. It generally uses large-scale text-paired data, like image or video captioning data found online. A common approach here is to keep the already pre-trained modules, such as the visual encoders and the core large language models, frozen.
Frozen, so their existing knowledge isn't changed.
Precisely. Instead, we only train that clever, learnable interface that connects these modalities. This strategy is incredibly effective for getting different senses to align without losing the valuable knowledge already embedded in the frozen modules. However, Some advanced methods do unfreeze more modules, perhaps the visual encoder, to allow for even deeper alignment if the specific task demands it. The data used here can range from massive, sometimes noisy web-scale datasets to finer-grained, higher-quality datasets often generated by powerful MLLMs themselves, though that tends to be more expensive. The second stage is instruction tuning. This is where we teach the models to understand and follow user instructions, which is absolutely crucial for real-world applicability. This significantly enhances their ability to generalize to previously unseen tasks and dramatically improves their zero-shot performance, meaning they can tackle tasks they've never seen before just from a clear instruction.
Right, that's key for practical use.
Exactly. Unlike traditional fine-tuning, which often demands huge amounts of task-specific data or simple prompting, which needs careful engineering for each task, instruction tuning helps the model learn to generalize across a wide variety of tasks simply by following natural language instructions. The data for this stage can be adapted from existing task-specific datasets like visual question answering sets, or, increasingly, it can be generated through self-instruction using powerful LLMs like GPT-4. Mixing different data types is also common, and the quality of this data, the diversity of prompts, and the breadth of task coverage are all absolutely crucial for success here. The final stage is alignment tuning. This is where the models are fine-tuned to align more closely with human preferences. A primary goal here is to reduce undesirable output, such as hallucinations.
Ah, yes, the hallucinations.
Mhm.
Very important to minimize those in medicine.
Paramount, where the model generates factually incorrect or fabricated information. Two key techniques for this are reinforcement learning with human feedback, RLHF, and direct preference optimization, DPO. Think of it like teaching. First, you show what's right through examples, that's supervised fine-tuning. Then with RLHF, you set up a system where the model gets rewards for good behavior, like positive feedback for accurate responses. DPO is a bit more direct. The model learns simply by seeing examples of what humans prefer versus what they don't, using a clever classification approach. Both methods aim to ensure the model's outputs are consistently helpful, honest, and harmless, which is, as you say, absolutely crucial in a sensitive and high-stakes field like medicine.
That gives us a solid technical grounding, painting a really clear picture of how these sophisticated models are built and refined. Now let's connect this directly to our audience, medical professionals. How are MLLMs specifically being applied in the medical domain right now, particularly in fields like oncology, perhaps, or medical education? What are the tangible benefits for you in your day-to-day practice?
Right. Well, if we connect this to the bigger picture, the advancement in large language models and multimodal models have immense potential to revolutionize oncology and medical education. Medical data, from electronic health records to advanced imaging, genomic analyses, it's all expanding exponentially. MLLMs offer an unparalleled way to process, integrate, and understand this vast and, frankly, previously siloed information. This allows for more informed decision-making and unprecedented innovation at every level of healthcare.
So are we seeing these models actually integrated into clinical practice already, or are they still largely theoretical, maybe confined to research labs?
We're certainly seeing significant exploration and early integration, even moving into real-world scenarios now. One common approach is training these models specifically on vast medical data sets. For example, BioBERT was an early success for biomedical text mining, showing strong capabilities there. More recently, Google's LLM, PaLM, was fine-tuned on medical data to create MedPaLM, which then advanced to MedPaLM 2. Now, this iterated model scored an impressive 86.5% on the U.S. medical licensing exam.
86%, that's remarkable.
It is. And this isn't just about passing tests. It demonstrates a remarkable level of knowledge encoding and reasoning capabilities in a genuine medical context, which is critical for patient care. Beyond exam performance, fine-tuned LLMs have proven capable of solving real-world problems, such as predicting clinical outcomes based solely on the unstructured text data found within electronic health records. That's incredibly powerful for busy clinicians, providing actionable insights from vast amounts of patient data that would be simply impossible for a human to manually process in the same time frame.
That truly is incredibly powerful, especially for busy clinicians juggling massive amounts of data. It sounds like a significant leap in deriving insights from patient records. What about applications that don't require such intensive, specialized fine-tuning on massive data sets? Are there easier ways in?
Indeed, there are highly effective alternatives. Generalist large language models can often be applied to medical tasks simply by using a detailed input prompt, effectively guiding the model to generate relevant medical information or analyses. But a particularly effective alternative is something called retrieval augmented generation, or RAG.
RRED. How does that work?
Well, Imagine you have a vast, up-to-date library of authoritative medical knowledge, perhaps all of PubMed or UpToDate. With R, when you pose a query, the system first retrieves the most relevant information from this trusted medical library. This domain-specific knowledge is then provided to a trained large language model in a machine-readable format. The model then generates an output based on your query and this rich, retrieved context. This allows it to leverage the most current, curated information without being explicitly retrained on it. It makes it incredibly flexible, reliable, and able to provide insights that are always up to date.
And how does multimodality, the ability to combine text with images or audio, specifically enhance these medical applications? Where does that added dimension really shine?
Well, that's where the true revolution often lies for medicine. Multimodal AI systems, capable of interpreting text and image data together, are already being evaluated for various critical applications in precision oncology, for instance, in complex outcome predictions. The fact that today's large language models are largely built upon transformer neural networks is key here. Think of them as incredibly flexible data processors. Their architecture makes them remarkably good at understanding and working with almost any type of data.
Whether it's text, images, or audio.
Exactly. Which is why they're so central to bringing different senses together in these MLLMs. These models, when pre-trained on large and diverse tasks and then applied to specialized ones, are often referred to as foundation models. In a clinical context, such models might be deployed as highly intelligent chatbot assistants to aid diagnosis interactively, perhaps bringing up relevant images or case notes as you query them. Similar successes are already seen in pathology, where vast image datasets are linked with contextual knowledge and case-specific information to achieve high performance in disease detection and biomarker prediction. They can even inform further diagnostic procedures, like recommending specific additional stains based on visual patterns. LabaMed, for instance, is an assistant specifically specialized in medical image understanding and question answering, built by instilling medical knowledge directly into a vanilla Eleva model.
It sounds like these models could significantly reduce the burden of manual annotation and data analysis, freeing up medical professionals for more critical tasks and, well, deeper patient engagement. That's a huge potential benefit.
Precisely. Foundation models can alleviate the need for incredibly time-consuming manual annotation and data interpretation, all while preserving, and in some cases even outperforming, traditional human-level accuracies. This is a potential game-changer for efficiency and resource allocation in healthcare. It allows clinicians and researchers to focus on more complex decision-making, direct patient interaction, and the nuanced aspects of care that, frankly, only humans can provide.
And what about the practicalities for healthcare systems? Are there considerations for deployment, especially for smaller institutions that might not have the extensive resources of larger academic centers? It sounds like these models could be very resource intensive.
That's a vital point, and it's something the field is actively addressing. There's a clear trend towards improving model efficiency, reducing model size, while crucially retaining performance. Recent advances with open source models, for instance, offer the prospect of developing new models with significantly lower financial and computational burdens. This makes them much more accessible for diverse medical institutions, including smaller clinics and regional hospitals, which is absolutely crucial for equitable adoption across the healthcare landscape. Beyond the current applications, there's enormous potential for even more advanced multimodal diagnostics and perhaps groundbreaking drug discovery. But to truly unlock this potential, it absolutely requires deeply collaborative efforts
Collaboration between who?
between medical experts in diagnostics and various clinical specialties, working closely alongside technology experts in both software and hardware development. This interdisciplinary collaboration is absolutely key to translating the raw power of these models into practical, beneficial tools for patient care globally.
This naturally raises a fundamental question, doesn't it? With such powerful capabilities, especially in a field as critical as medicine, what are the ethical considerations we absolutely must address? We've heard about AI hallucinations and bias in other fields. How do these manifest in medicine where the stakes are so incredibly high?
Indeed, while the potential is vast, the ethical challenges are equally significant. Biomedical ethics is founded on four core principles: autonomy, non-maleficence, beneficence, and justice. The widespread use of large language models, and by extension multimodal large language models, in medical education and clinical practice directly challenges these foundational principles. We must navigate these very carefully to uphold patient trust and safety.
Let's start with privacy and data. Patient data is incredibly sensitive. What are the specific risks LLMs introduce here, given their vast appetites for information?
Privacy and data security risks are paramount. Large language models, with their enormous parameter sizes and vast training data sets, can inadvertently memorize sensitive personal information from the data they've been trained on. Studies have confirmed the tangible risk of privacy leakage, even during the inference process when a model is simply responding to a query. And even if data is initially anonymized, advanced models can potentially re-identify personal information through sophisticated linkage attacks.
Linkage attacks, how does that work?
Well, research has shown that by using as few as 15 demographic attributes, these models can re-identify up to 99.98% of personal data in an anonymized dataset.
99.98%, that's almost everyone.
It's a staggering figure. And this presents a huge challenge when using large language models for sensitive tasks like clinical case discussions or interpreting imaging data, which are inherently rich with patient-specific information. Furthermore, the reliance on cloud servers for training and user data storage creates security vulnerabilities that could lead to sensitive information leakage. It's also worth noting that large language model development companies often retain rights to use and share user data for service improvement, which, further exacerbates these privacy risks.
That's deeply concerning for patient trust. And what about AI hallucinations, where the models generate inaccurate or fabricated information? In medicine, as you said, this could be catastrophic. What does that actually look like for a medical professional or student using one of these?
This is a major obstacle, and in medicine the implications are indeed profound. AI hallucinations mean that large language models generate responses that might appear logical or plausible, but are in fact incorrect, inconsistent, or fabricated. This can even include forged references to non-existent studies or authors.
Really? Fake references?
Yes. Studies have already shown significant error rates in medical contexts. For instance, between 17.5% to 27.5% in answering lung cancer questions, and they can offer vague, outdated, or outright inaccurate information in dentistry. The root causes of these hallucinations are multifaceted. Firstly, the training data is often sourced from the internet, which can contain outdated, inaccurate, or poorly quality-controlled information. Secondly, there's restricted access to authoritative, up-to-date medical databases like PubMed or UpToDate due to subscription barriers, which limits the model's ability to obtain truly reliable and current research data. Finally, the inherent probabilistic nature of text generation in these models also contributes. They are guessing the next most likely word, not stating facts per se. The one-to-many model of large language models means that if unverified erroneous content is generated and then used in medical education, it can propagate widely and rapidly. This directly impacts students' foundational knowledge and their future clinical decisions, potentially leading to systemic errors in patient care. It fundamentally undermines academic rigor and erodes public trust. Research sadly highlights that less than 70% of AI-generated fictitious abstracts were identified by peer reviewers, demonstrating just how convincingly these errors can be presented.
Less than 70% identified. That's worrying. And biases in the training data and algorithms, how do they manifest and impact fairness in medical education and care? We're talking about real-world health disparities here, potentially worsened.
Bias in training data is a direct cause of skewed outputs, and it's a critical ethical concern. If large language models are trained on data containing biases related to sex, race, culture, or socioeconomic background, they will inevitably replicate and potentially even amplify these biases. For example, a chest X-ray classifier trained mainly on data from white patients showed poorer recognition capability for non-white patients. As the volume of large language model-generated content increases online, and if that content is subsequently used as further training data, it could inadvertently reinforce existing biases, creating a harmful feedback loop.
A feedback loop of bias, that's not good.
Not at all. Algorithmic bias further exacerbates the problem. During the design and optimization, if the goals and evaluation criteria primarily focus on the majority population, the specific needs of minority groups can be neglected. For instance, if an LLM is trained predominantly on Western alcoholic cirrhosis cases, without sufficient data on hepatitis B-induced cirrhosis prevalent in other regions, it may provide inaccurate guidance for the latter. This perpetuates unfairness in clinical practices and, crucially, can distort students' ethical concepts during their training. This can lead to misdiagnoses or inappropriate treatments for diverse patient populations, directly violating the core principles of non-maleficence, beneficence, and justice.
The black box effect of LLMs, where the internal logic is opaque, must also be a significant concern in a field demanding such high accountability and transparency. If a diagnosis is suggested, a doctor needs to understand why.
Absolutely. the lack of transparency and interpretability is a significant barrier. It means that users, whether they are educators or medical professionals, often cannot comprehend how a particular response from an LLM was generated or the underlying logic behind it. This opaqueness is primarily due to the incredibly complex model structures and the vast, intricate training data sets, which make their internal operations extremely difficult to understand. In a medical context, where understanding the why behind a diagnostic decision or treatment recommendation is absolutely critical for patient safety, for professional development, and for legal accountability, this black box nature is a profound concern. It hinders trust and makes it challenging to identify and rectify potential errors effectively.
We also hear a lot about AI's lack of emotional intelligence. For medical professionals, empathy is such a cornerstone of care. How does LLM use affect this, particularly in scenarios where human connection is so vital?
Well, while large language models can certainly be trained to provide seemingly empathetic responses, and some studies even suggest they can appear more empathetic in certain text-based consultations than human professionals, this artificial empathy cannot truly replicate the subtle genuineness of emotions conveyed by healthcare professionals. Crucially, LLMs cannot perceive nonverbal cues like tone of voice, facial expressions, or body language, which are absolutely fundamental to human emotional understanding.
Right, the things you pick up in person.
Exactly. Their empathy is limited to textual descriptions, whereas real empathy often involves physical gestures and a nuanced responsiveness to complex, uncertain real-time interactions shaped by diverse patient backgrounds, beliefs, and values. Over-reliance on LLMs for direct patient interactions, or even in teaching scenarios like medical history collection or perhaps disclosing difficult conditions, could inadvertently reduce the presence of genuine human empathy in clinical environments. This directly conflicts with the goals of medical ethics education, as the development of empathy requires ongoing practice in diverse, emotionally rich settings, something that static LLMs simply cannot provide. It risks fostering a generation of professionals who might be less adept at truly connecting with their patients on a human level. This leads us to educational fairness. Can large language models, ironically, exacerbate disparities in medical education despite their potential to democratize information and knowledge? Yes, it's very much a double-edged sword. On one hand, LLMs certainly have the potential to aggregate rich teaching resources globally and offer relatively equal learning opportunities, particularly perhaps to remote regions, and even enable non-native speakers access through cross-language support. However, the reality is that institutions with better technological infrastructure, higher budgets, and access to the most up-to-date technologies will find it far easier to harness these benefits. In contrast, schools and regions with limited resources might face exacerbated inequalities. This can be due to inability to afford the technologies, lack of professional knowledge for implementation, or even restrictions on access like ChatGPT being unavailable in China, for instance.
So the digital divide gets wider.
Potentially, yes. Moreover, the extensive data processing required inherently exposes data to privacy and security risks. Institutions lacking sufficient resources and robust infrastructure may struggle to adequately safeguard user data, increasing risks. Ultimately, this can lead to academic disadvantages for students and researchers lacking access, creating a new form of disparity in an age where information access is key.
Academic integrity is another huge area. How do LLMs challenge the very foundation of how medical students learn and conduct research? The implications for trust in medical knowledge seem significant.
The issues of plagiarism and cheating are significantly amplified, it has to be said. These models can summarize articles, assist with data analysis, retrieve literature, or even generate entire draft papers. Studies have shown, as I mentioned, that university professors struggle to distinguish LLM-generated abstracts from human-authored ones. This indicates the quality of text has reached a professional level, creating significant opportunities for academic misconduct.
So students could just submit AI work.
Well, they might use it to generate abstracts, data, or even complete papers, leading to suspicions of plagiarism, regardless of the content's originality. There have been instances of articles being retracted due to direct replication of LLM-generated content. Furthermore, the high accuracy of LLMs on medical examinations, successfully passing things like the USMLE, creates clear opportunities for cheating. Excessive reliance on these tools can unfortunately decrease students' critical thinking, research ability, innovation, and perhaps their intrinsic motivation to learn. This risks fostering a vicious cycle of academic misconduct and the widespread dissemination of potentially erroneous information, severely impacting the rigor and trustworthiness of medical education.
And finally, the crucial questions of responsibility and copyright. When an LLM makes an error leading to patient harm, who is accountable? This is incredibly complex for clinicians. And who owns the content it generates, given so much of its training data is copyrighted?
From a legal perspective, AI currently lacks the legal standing of a human. This means that humans remain the ultimate accountable parties. However, in complex medical settings, the specific responsibility for patient harm due to LLM biases or inaccuracies is currently, well, unclear. This ambiguity affects everyone: individual doctors, patients, institutions, and the LLM developers themselves. Developers like OpenAI often explicitly disclaim responsibility for the texts generated in their terms of use.
So they wash their hand of it?
In effect, yes, the legal frameworks haven't fully caught up. This leads to significant ambiguity and responsibility attribution and regulation in real-world applications. On the copyright front, there are equally complex issues. LLMs are trained on vast amounts of text, much of which is copyrighted. There are ongoing legal questions about whether this constitutes fair use or if it infringes copyrights. This is a topic of active litigation, with various authors and publishers pursuing legal action against AI developers for alleged mass copyright infringement.
Right, I've read about those cases.
Exactly. There are also significant concerns about whether content generated by LLMs can itself be copyrighted, and if so, by whom. Furthermore, how do we prevent unauthorized use or infringement when LLMs can so easily mimic existing styles or generate content closely resembling copyrighted works? These questions directly impact creators, knowledge holders, and the models themselves, demanding urgent clarity and new legal frameworks.
It's clear that these challenges are incredibly complex and deeply interconnected, so how do we address them? What does a robust ethical framework for large language models in medical education and clinical practice truly look like? We need a clear roadmap forward, surely.
To integrate LMs responsibly and safely into medicine, we absolutely need a unified ethical framework specifically tailored for their application, particularly in medical education. This framework should be deeply grounded in those four core biomedical principles: beneficence, justice, autonomy, and non-maleficence. Building on these, we propose 8 fundamental principles, each with specific, actionable implementation methods. The big idea is ensuring these powerful tools enhance care without compromising our core values.
Let's delve into these 8 principles then. First, how do we ensure privacy and data protection in this new landscape, especially with such sensitive patient information? What are the practical steps?
Right, it requires a multi-layered approach. Firstly, the core idea is multi-layered privacy protection mechanisms. This involves employing advanced de-identification techniques, like generalizing sensitive information, and also differential privacy, which adds noise to the data to prevent re-identification. Secondly, robust data encryption and secure storage are essential, using tamper-proof hardware and distributed storage systems to protect data both in storage and during transmission. Thirdly, we must establish strict data usage policies. These policies must ensure data providers, especially patients, have control and transparency. Users must be explicitly informed and able to withdraw consent. And finally, strict access controls are non-negotiable. Implementing multi-factor authentication and stringent controls ensures only authorized personnel access sensitive data.
And to combat those hallucinations and ensure reliability, which, as we discussed, can be catastrophic in medicine, what about data quality control and supervision? How do we build trust in the information these models provide?
This is absolutely critical. Firstly, the idea is to develop independent, curated LLM databases. This means all training data should be meticulously reviewed by clinical experts before incorporation, ensuring authenticity and accuracy. LLM-generated content also needs regular, rigorous review to identify and correct biases or errors promptly. Secondly, a crucial link to authoritative databases is necessary. Integrating with and regularly updating from credible sources like PubMed and UpToDate ensures accuracy and relevance, enhancing credibility. Lastly, fostering a critical approach is paramount. Educators and students must be explicitly taught to critically assess all LLM-generated information, verifying it against established medical knowledge, maybe even other LLMs. This cultivates high-quality standards.
So it's about rigorous vetting of the data in and the outputs out. That's crucial. Now, regarding fairness and equal treatment, how do we proactively mitigate the biases we discussed earlier to avoid worsening existing health disparities?
To eliminate health disparities, we must be proactive. The core idea is diverse and comprehensive training data. Developers must use datasets that are truly diverse, actively filtering out discriminatory factors. Second, we need fairness review and monitoring mechanisms built into deployment, regularly evaluating and detecting biases in model outputs, making adjustments as needed. Third, promote open and accessible resources. Initiatives providing broad access to LLM resources can help democratize their benefits. And finally, fostering cross-regional and cross-economic collaboration is essential to address infrastructure and knowledge disparities, ensuring benefits reach everyone.
For the black box issue, where the internal logic is so opaque, what about transparency and interpretability? How can we make these complex systems more understandable for medical professionals who need to trust their outputs?
Enhancing understanding and trust is key. The big idea is clear communication. Firstly, comprehensive model documentation and operational guidelines are indispensable. Developers should provide detailed explanations of mechanisms, processes, logic, including design objectives, data sources, limitations. Secondly, we must implement interpretative interfaces or tools. These tools allow users to understand the model's reasoning in real time, perhaps visual tools tracing data processing.
So you can see how it reached the conclusion.
Potentially, yes. That's the goal. And thirdly, regular public evaluations and feedback mechanisms are crucial. Involving external experts and users in regular evaluations with effective feedback channels promotes continuous improvement.
Moving to academic integrity and moral norms, how do we protect these in an LLM-augmented educational environment? This feels vital for cultivating critical thinking and empathy in future medical professionals.
Absolutely vital. The core idea is ensuring LLMs augment, not replace, human intellect and ethics. Firstly, educational institutions must establish clear policies and guidelines for LLM usage, defining legal and ethical use and prohibiting academic misconduct with clear consequences. Secondly, we need to develop and use effective detection tools to identify and prevent plagiarism or inappropriate use, ensuring originality. Thirdly, educators must maintain their leadership roles, guiding students to critically analyze LLM content, emphasizing models or auxiliary tools, not substitutes for human thought, encouraging questioning and verification. And finally, perhaps most importantly, we must foster empathy and compassion. Through rich interpersonal interactions and clinical practice, leading by example, educators must enhance students' humanistic aspects, promoting understanding and respect for patient emotions. Empathy needs practice in real settings.
Those are powerful principles for shaping future practitioners and for the crucial aspect of accountability and traceability when an error occurs that impacts a patient who is ultimately responsible. How do we establish clear lines here?
Ensuring clear responsibility is paramount. The idea is a clear responsibility framework, defining clear roles for developers, deployers, and users. Developers ensure design meets standards. Deployers ensure compliance. Users make and verify professional judgments, retaining ultimate accountability. Secondly, detailed logging and monitoring systems must be implemented. Recording input, outputs, decision paths allows robust traceability if issues arise. Thirdly, independent review committees should be established, committees of technical, legal, medical experts to investigate issues from LLM errors and recommend improvements. And finally, providing clear complaint and feedback channels for patients and users is essential, allowing them to report harm and seek help promptly.
And what about intellectual property protection? It's a minefield, as we discussed. How do we navigate that?
Strict measures are needed. The core idea is adherence to legal and ethical norms. Firstly, strict IP compliance processes, ensuring LLMs use only authorized or publicly licensed data with meticulous documentation and reviews. Secondly, clear copyright statements and terms of use for LLM-generated content, ensuring users comply with IP laws. Thirdly, effective monitoring and detection systems to identify and prevent unauthorized use and potential infringement, perhaps flagging content and outputs. And finally, complaint and feedback mechanisms for creators and IP holders to report and address infringement issues promptly.
Finally, amidst all these crucial safeguards, how can we leverage LLMs to actively promote educational research and innovation responsibly within medicine? How do we keep pushing the boundaries, but in a safe way?
The framework should actively encourage this. The big idea is continuous improvement through responsible innovation. We should be optimizing teaching content, regularly monitoring and evaluating recent medical findings and clinical practices. LLMs can then be instrumental in integrating these latest insights into the curriculum via LLMs, ensuring it remains current and promotes continuous improvement. It's about harnessing the technology to continuously elevate the quality and effectiveness of medical education, fostering innovation while always adhering to these vital ethical safeguards. It's a dynamic process.
That's been an incredibly comprehensive deep dive into multimodal large language models and their profound implications for medicine. It's clear that while the technological promise is immense, particularly for mid-senior professionals like you listening, the ethical challenges demand our proactive and thoughtful attention. The idea of a unified ethical framework building on those 8 fundamental principles feels like the crucial next step forward.
Indeed. This isn't just about technological advancement. It's about ensuring that medical education and practice evolve without compromising the core principles of fairness, justice, and patient safety. That balance between innovation and ethical safeguards is really what will define a safer and more efficient environment for future medical professionals and, of course, their patients.
What stands out to me is how these models could transform everything from diagnostic assistance right through to the way medical knowledge is disseminated and applied. The ability to integrate and reason across different modalities is genuinely revolutionary. It really makes you think about how our roles in healthcare will inevitably evolve.
Absolutely. And if we connect this to the bigger picture, the ultimate goal has to be to empower, not replace. These tools, when developed and applied ethically, can truly augment human capabilities. They can allow medical professionals like you to focus on the truly human elements of care, the complex decision-making, the nuanced interactions, the essential empathy that defines our profession. Imagine the potential for you to spend more time with patients and perhaps less time wrestling with data.
A truly thought-provoking discussion. Thank you. To you, our listeners, if you found this deep dive as insightful as we did, please do take a moment to rate and share Deep Dive Ortho with your colleague. It really helps us continue to bring these vital conversations to you. Until next time, keep questioning, keep learning, and keep thriving in this ever-evolving world of medicine.